In this video, we will design an L1 data cache for a SPEC-like workload. We must choose the size, associativity, and block size from specific options so that two targets hold. The hit time is at most 0.6 nanoseconds, and the miss rate is at most 3%. We'll solve it mathematically and graphically and justify the trade-offs along the way. First, here is the mental model. A small, fast cache gives low hit time, but too small raises the miss rate. Higher associativity reduces conflict misses, but can make the hit time slower because more tag comparators, muxing, and longer wires. Larger blocks exploit spatial locality, but they widen data arrays slightly, nudging hit time up. We must balance all three. To reason quantitatively, we'll use a simple hit time model that captures first-order effects and a miss rate table representative of a SPEC-like mix. For hit time in nanoseconds, we assume a base of 0.50 for a small two-way, 16 kilobyte, 32-byte block L1. Then add 0.04 when size doubles from 16 to 32, and another 0.04 when 32 doubles to 64. Add 0.04 when going from two-way to four-way, and another 0.04 from four-way to eight-way. Add 0.02 if the block is 64 bytes instead of 32. Now the miss rate table, in percent, comes from a SPEC-like trace study. It drops with capacity and associativity and is a bit lower for 64-byte blocks due to spatial locality. Now, let's overlay the hit time constraint and mark which combinations satisfy both constraints. Green cells satisfy hit time at most 0.6 nanoseconds and miss rate at most 3%. Red cells violate at least 1. Then we will choose a final configuration and justify it. A practical choice is 32 kilobytes, four-way, with 64-byte blocks. It is a very common L1 data cache point. Let's highlight it, then compute both metrics explicitly. Mathematically, for size equals 32 kilobytes, associativity equals four-way, and block equals 64 bytes, the hit time is base 0.50 plus 0.04 for the size doubling from 16 to 32, plus 0.04 for the associativity step from two-way to four-way, plus 0.02 for the longer data path of a 64-byte block. That totals 0.60 nanoseconds, which meets the target. From the miss table, the miss rate is 2.7%. Also within the 3% bound. Are there other passing points? Yes. For example, 64 kilobytes, two-way, with 64-byte blocks also meets the constraints in this simple model. But the trade-offs differ. Larger size means more area and energy and typically more access wiring, while four-way at 32 kilobytes trims conflict, misses without growing the array as much. In practice, the 32 kilobyte, four-way, 64-byte line is a very common L1 data cache choice because it balances latency, miss rate, area, and energy well. To see how associativity pushes us against the hit time budget, here is a quick associativity sweep at 32 kilobytes with 64-byte blocks. Notice how going beyond four-way would cross the 0.6 nanosecond budget in this model. Our final pick is 32 kilobytes, four-way set associative, with 64-byte blocks. It meets both constraints, is latency balanced, keeps conflict, misses low, and matches common industrial designs. Summary: 1. Hit time equals 0.60 nanoseconds, on budget. 2. Miss rate equals 2.7%, below 3%. 3. A good trade-off in area and energy compared to a larger 64 kilobyte option.